All right, number one is just practicing writing out the rules. Let me start with number two. All right, position function is given by f of t. We see a trig function with an exponent that's written in that shorthand form, so it's always a good idea to rewrite it with a set of brackets. Okay, find the average velocity or average rate of change. So we know average velocity doesn't require the velocity function. All it requires is the slope between two endpoints of the position function. So average velocity is change in position over the change in time. So let's find f of 0 and f of pi over 4. Sine of 0 is 0, 0 squared is 0, 0 times 0 is 0 times 2 is still 0.
Why did you do 3 pi over 4? Not pi over 4.
It was pi over 4, but then I'm putting it in for t.
Oh, okay.
So I'm multiplying by 3. And by the way, a value is my 0, b value is the pi over 4. So sine of 3 pi over 4, we know that's in that pi over 4 family. Sine and cosine are both root 2 over 2, but sine is going to be positive in the second quadrant. So root 2 squared is 2. 2 over 4 is 1/2. 1/2 times 2 is 1. So therefore, f of 3 pi over 4 minus f of 0 over 3 pi over 4 minus 0. And just finding slope between the two endpoints. This ends up being 1 minus 0. I'm sorry, not 3 pi over 4, my bad. I had 3 pi over 4 as the function, but then I'm back to pi over 4 if I'm doing my b value. So 1 divided by pi over 4, the same thing as flipping that pi over 4 up as the reciprocal, that's 4 over pi. So my average velocity is 4 over pi, units of measure, meters per second. Okay. Part B, at what time does the instantaneous velocity equal the average velocity? So this is really asking us to set up essentially mean value theorem, because mean value theorem is the average rate of change equaling the instantaneous rate of change. So we have average rate of change, and the instantaneous rate of change is just the derivative, right? So we're asking the derivative essentially to find us the place where the graph is going to experience this exact velocity. But we're just setting up the equation, we're not solving. But let me just set up what we're doing with mean value theorem here. We already have most of it. So we have this piece, right? We have the slope. We just need to find the derivative, which in this case is the velocity. So to find the derivative, we have to go through chain rule here, outside, inside. Okay, so f prime, outside's derivative, 4 bracket to the first power. We keep the inside portion unchanged. Now that we're done with the outside's derivative, we move on to the inside portions. Sine u's derivative is cosine of u times u prime. Okay, so now mean value theorem, we're just doing this, right? We're setting the average rate of change equaling to the instantaneous rate of change. We're just setting them equal to each other. Now, if we were to solve for t, which I'm not going to ask you to do it unless it's a little bit simpler than this, then we would essentially find the moment in time when this particle is going to reach this exact velocity. Part C, on the interval from 0 to pi, when does f of t equal to 1, or when is the position equal to 1? So we're just basically setting f of t equal to 1 here. Okay, so we're going to clean things up here, maybe involve inverse trig so that we can eventually make our way down to that t. So I'm going to divide both sides by 2 first. And then I want to undo that square. So I need to take the square root of both sides. If I take the square root of both sides, plus or minus shows up. Zoom in a little bit. Now, plus or minus 1 over root 2 is the same thing as root 2 over 2. So maybe if I write it that way, feels a little bit more familiar. All right, I want to solve for t. Let me move that sign over and make it inverse sine.
Wait, is that
Yeah, root 2 over 2. it's the same thing as 1 over root 2. I just wrote it in this way. Maybe it feels more familiar in terms of unit circle values. So this is basically saying what theta values allow sine to be equal to plus or minus root 2 over 2, right? And this is all going to be all the power 4 family, right? First quadrant, second quadrant, third quadrant, fourth quadrant. So I'm going to list all of them out. Okay, so yeah, this is just basically asking what theta values is sine equal to plus or minus root 2 over 2. So theta, pi over 4, 3 pi over 4. Now, these values are going to shrink because I got to divide by 3. I'm going to extend this out and go past 2 pi because eventually when everything shrinks, I want to list out all the possible values between 0 and pi. So if I add 2 pi to each of these, if I add 2 pi to this, I'll get 9 pi over 4 plus 2 pi. If I do 3 pi over 4 plus 2 pi, essentially it's 8 pi over 4 plus 8 plus 3 pi over 4. And 5 pi over 4 plus 2 pi. And then 7 pi over 4 plus 2 pi. Okay, so let's say if I didn't do that, then let's say I just stopped here at 7 pi over 4. Okay, I want to solve for t, but I'm going to have to divide by 3 here, which is the same thing as multiply by 1/3. So t is equal to pi over 12, 3 pi over 12, 5 pi over 12, and 7 pi over 12. Right? If I didn't do the rest, I would just stop here. But there's still some gap here. There could be more t values that still live between 0 and pi. So I have to go a little further out because all these values are going to shrink, but I want to have all the values extending out to pi at the end.
How far out do you go still?
Well, this is, I mean, we should be able to get to the point where we're really, really close or we're 1 over. If we're really, really close or 1 over, then we know we can stop. Essentially, when your numerator and denominator are really close to each other, that's basically when it's reaching close to pi. Yeah, once we reach this, we know we've gone over, right? We've gone over pi, so we can remove that. Here are t values. Okay, related rates. Cyclist A is traveling east. Cyclist B is traveling south. So cyclist A is basically heading towards the intersection. And so we can expect this to be decreasing over time. I'm going to call this X. But then as cyclist B travels away from the intersection, is causing this length to increase over time. Yeah, I'll specify on the test but basically X is the horizontal and Y is the vertical. Yeah. Yeah. So part A, find the rate at which the distance between the two cyclists are changing. So essentially we're having to deal with Pythagorean theorem, and we're going to eventually work towards finding that rate of change between A and B, which I'm going to call Z, since those are our familiar variables for Pythagorean theorem. So find the derivative. List out all of our variables here. All right, cyclist A travels east 15 miles per hour, but it's closing in. So we know that rate is going to be adjusted to be a negative, so negative 15. Cyclist B travels south. As he travels south at 20 miles per hour, he's causing this Y value to increase over time. So we want that rate to be a positive. We're looking for dz dt. X is 8, Y is 15. And then we want to find the Z at that moment in time. So Pythagorean theorem, A squared plus B squared equals C squared. Ends up giving us 17. Yes.
Could you explain then why the 15 is negative?
Right. So what's happening to this length as cyclist A is heading towards the intersection? Is that length getting longer or shorter? So he starts off here, but then he's going to be here and then moving here to here to here. So what's happening to this distance? Yeah, it's getting, so if your value is getting smaller over time, the rate will be negative. I'm sorry. The intersection of the two roads is right here. Right.
Thank you.
Meanwhile, if the triangle was drawn a different way, it was drawn like this, and let's say A was going this way and B was going this way, then all of a sudden he's causing that distance to increase. So then this problem, the rate will be a positive.
Okay.
So yeah, so if you can visualize the problem in motion and just convince yourself, is that value getting larger or is that value getting smaller? And that will help you decide whether to keep that rate positive or negative.
And also, should we keep our calculators in like degrees or radians?
It's always radians, yeah.
Okay.
Always radian. But I think for our purposes, it's not going to make a difference because we're not solving for theta, we're doing ratio here.
Oh.
So, but for future reference, it's always radians. Okay, so now we plug everything in. Sorry, I don't know why this is now. I'll be right back. Yeah. And then get stuff set.
On the last problem, uh, 2C, use the inverse trig to move that that 3t out and the sign of like.
Yeah, I wanted to separate things here. I want to solve for 3t, but that sign is out of place here. So I want to move that sign over. When I move that sign over, it becomes inverse sine.
Okay.
And inverse sine is basically no longer looking for the ratio. I'm looking for the theta values or the radian measures.
So you can just like basically like add the inverse sign and like switch them around.
Right. It's kind of like dividing, but not really. It's kind of just moving that trig.
But also, how did you know that was gonna be root 2?
Right. So
Just the-
yeah, 1 over root 2. If I were to rationalize that denominator, it ends up being root 2 over 2. I just wrote it this way because this feels more familiar from a unit circle perspective. Yeah. Okay, so any questions, part A? Part B, at what rate is theta changing at that moment? We're going to rely on x and y to build out our trig function. So that's going to be opposite over adjacent. So we use tangent. Find the derivative, quotient rule on the right side. Prime g minus fg prime.
Why did you call it? Just know what you usually do.
I will when I build my second triangle. But right now, I do need to hold on to these variables as I build my equation. Otherwise, I'm stating to the problem that these numbers never change, which is not true, right? We know that the cyclists are still moving, so we do need to hold on to these variables. Well, yeah, but once we find the derivative and we're ready to make our substitution, we'll create a second triangle with that moment in time built in. So we have all the values that we need from above. We have x and y, we have dx dt, we have dy dt, so they all get inserted into these locations. And the last thing we need to do is having to figure out what to replace sec and the theta with. So we can create a second triangle with all the values filled in for this moment in time. So at this moment in time, x is 8, y is 15, and z is 17. So we're going to use this information to help us find a replacement for secant and theta. So secant is related to cosine. Cosine is adjacent over hypotenuse, right? So therefore, secant will be hypotenuse over adjacent. So 17 over 15 will replace that secant, but we got to square it as well. Does everybody see the path to filling those variables with values? So once we replace secant theta with 17/15, that becomes 17/15 squared. Dx dt gets replaced with -15, y is 15, x is 8, dy dt is 20, and y is 15, but we do 15 squared. We can plug all this in the calculator here. We can isolate d theta dt, so dividing by 17/15 squared, the same thing as multiplying by 15 squared over 17 squared. Put all that in, we should get negative 1.332, and then radians per hour. Say that again. Yeah, I think this is the reduced version after I multiply everything and divide it out. Yeah. Yeah, so I think what's happening is that the 225 and 15 squared will end up canceling out. We're just left with this over that. That's why. Okay, any questions with related rates? Okay, next. Find dy dx for this equation. Multiple things are going on here. There's implicit. You see multiple y's that we have to account for. We see product rule here as well. And finally, we have to get this with brackets with inside-outside portions. So there's also a chain rule. Oh, sorry. Yeah, you're right. It should be too high. All right, so we'll go through product rule here. Cotangent u becomes negative cosecant squared u times u prime. Y becomes 1 dy dx. Oh, by the way, we have 3 y variables, so we should be expecting 3 dy dx's along the way. I think that 1 is helpful. Later on, when we factor that dy dx, that 1 is a reminder there's still something left. Doesn't completely go away. All right, this is chain rule here. bracket to the 5 halves becomes 5 halves, bracket to the 3 halves. So now that we're done with the outside portion, we move on to the inside. Tangent of u becomes secant squared of u times u prime. 5y squared becomes 10y dy dx. And then the 0 goes, sorry, 7 goes to 0. My bad. 3x becomes 3, and then the 7 goes to 0. Let me change that. So I have 3 terms that have dy dx in them. So I'm going to add and subtract in a way where each of these can be on the same side of the equation. And then all the non-dy dx terms, they will all go together on the other side. So I'm just doing a little bit of cleanup here. I made this 5 halves times 10 as 25. I like to pull the non-trig in front. So I'll move this over to the left side, keep these on the left side, and then the cotangent, the 2y, and the 3 will go on the right side. So these are the 3 terms that, let me zoom in, are the 3 terms that have dy dx in them. And now I can just factor out the dy dx and then bring all that mess over to the other side. And also, if you didn't simplify these terms here, it's okay. I just merged some of the values together, but you didn't have to. As long as your dy dx is by itself. Yeah, 3303. Thank you.
On the test, if we do MBT, do we have to write down the conditions?
If only if there's a mention of can mean value theorem can mean value theorem be applied, then go through the conditions. Yeah, so conditions are continuity with brackets and differentiable with parentheses. All right, number 5. So we have to involve product rule, x cubed inverse cosine of pi x. We have to remember our derivative rule for secant, and also our derivative rule for arc cosine, right? So arc cosine, inverse cosine, that's the new set of rules that we've learned. And the derivative of arc cosine looks like arc sine. It's just with the negative in front of the u prime. So negative u prime over the square root of 1 minus u squared. So we set up using product rule. Okay, f prime g plus fg prime. So f prime x cubed becomes 3x squared. G stays as inverse cosine of pi x. Back to f x cubed. And then now we got to activate our cosine's derivative. So my u value is pi x. So negative u prime would be just negative pi all over 1 minus u squared. So pi x quantity squared. Next up, secant of u's derivative is negative secant u tangent u times u prime. And then 5 pi e squared. There's no variables here. Pi is a number. E is also a number. Any number is still going to be a constant. Constant's derivative is going to be 0. Okay, any questions here? I'm going to come back to number 6 if I have time. Number 6 is just same thing as 2C, number 2, part C, where you're just doing inverse trig, listing out all the unit circle values and then dividing and solving for t that falls between the interval. I want to do a curve sketch. This is basically the same one that we did yesterday, but because it's going to look like it, I want us to do another run through this problem here. So first thing, we start off with finding derivative because we just want to find our critical points so that we can populate our f prime sign line. So my f prime is just 1/2 plus sine of x. I just want to know when is f prime going to be equal to 0. So essentially, when is sine of x equal to 1/2? Sorry, negative 1/2. So third and fourth quadrant. But if you think about where these values live to the right of pi. So it doesn't quite fall inside that interval. So we subtract 2 pi from these to see if we can find any coterminal angles that live between negative pi and pi. We're going to find them by subtracting 2 pi. Essentially is minus 12 pi over 6. Sorry, negative 5 pi over 6 and negative pi over 6. Our graph is always going to be oscillating. So if I just test 1 or 2 numbers, I should be able to figure out the pattern here. So if I plug 0 into my derivative, 1/2 plus sine of 0, it's going to be positive. Great, thank you. If I plug in negative pi over 2 in for x, that's basically saying same thing as sine of 3 pi over 2. We know sine of 3 pi over 2 is negative 1. Negative 1 plus 1/2 is negative. It's hard to find one here, but you can sketch your original function in your calculator. You can also see that sine and cosine will be oscillating. So next up, plug these values back into the original function to get your order pairs. And then once you use your unit circle value to get your order pair, even if they're not easy to interpret where those values are, you can just plug those in the calculator to get some idea where the decimal approximation is. Okay. From there, we'll repeat the process and move on to f double prime. So f prime is 1/2 plus sine x. So f double prime will just be cosine of x. And we find our critical points at the f double prime level, set cosine of x equal to 0. Normally, we would say pi over 2 and 3 pi over 2, but 3 pi over 2 doesn't quite land inside the interval. So if I subtract 2 pi to see if anything fits, we get negative pi over 2. So our candidates are now negative pi over 2 and pi over 2. So anytime you're testing your sine line, you're going to be plugging values into that derivative that you're working on. So we're working on a second derivative. So we're going to plug 0 into the second derivative. So 0 and for cosine is positive. I want to see it initially that you're using your unit circle knowledge, but then after you do this, then you can plug in the calculator. It's for graphing purposes. But for these, you don't have to show the work in terms of whether the slope is positive or negative. But for the relative max, relative min, I do want to see these order pairs are. Show me how you got to the y value, like if you didn't have a calculator, and then you can use your calculator after that.
Wait, I thought.
Well, if I'm trying to find relative max, relative min, they go back into the original equation. if I'm testing my sine lines, they go into the derivative that I'm working on. So here I tested between pi over 2 and pi. You can choose anything in the second quadrant. I chose maybe 2 pi over 3. And I convinced myself that cosine in the second quadrant is negative. And this is basically in the third quadrant. Cosine in the third quadrant will be negative as well. So because of the change in sign, we know these are points of inflections. Plug them back into the original equation to get their y values. And then once you have all your y values and the y values at your endpoints, you can start thank you. You can start to sketch them onto the graph. You have your calculator to help you, but also let's make sure we know how to write all of our because statements as well. Min is because f prime changes from negative to positive. Max is because f prime changes from positive to negative. Point of inflection is because f double prime is changing signs. I didn't specify increase and decrease, but if I were asking you for increase, decrease. And that's just reading off of the sign lines of those increase or decrease.
I thought the relative min would just be negative pi over 6. Because that's like on like our side line that we did. That was the only time I went from negative to positive.
Yes, that's right.
So, okay.
How do you know what's like the absolute max and min?
Oh, absolute max and min. You just look at your graph. The highest point is your absolute max. Lowest point is your absolute min.
But don't you have to, oh, like when you plug it in?
Yeah, when you plug in or when you sketch your graph. Yeah, your absolute max, absolute min is just the highest and lowest points overall. The highest y value and the lowest y value that you see on your graph.
Okay.
We go for number 6 as well. Okay, let me just quickly go over number 6. This is just same thing as 2C, number 2, part C, where you're just trying to eventually solve for t. So divide both sides by 2, bring that cosine over, that's inverse cosine. So if we can figure out this piece first, so basically we're asking, when is cosine of theta equal to 1/2? So cosine of theta is equal to 1/2 at in the first and fourth quadrant, so pi over 3 and 5 pi over 3. And then because I know I eventually have to divide something out, they're gonna shrink, and we wanna go further out. So I can just keep adding 2 pi, or in this case, 6 pi over 3, so that I can match the denominator there. So 1/3 plus 6/3 is 7/3, 5/3 plus 6/3 is 11/3. I just went a little further out than I potentially needed. And then dividing by 5 pi over 2 is same thing as multiplying by 2 over 5 pi. If I divide everything, divide this or multiply by reciprocal through everything. And I'm just looking for my resulting values to live between 0 and 2. And anything that's between 0 and 2, I keep. Anything that's outside, I once I go past 2, I can stop. Right, let me know if you have any individual questions for me. So.
I was thinking the same thing. I feel like it has to be from the equation, right? Like we plug something in. I would believe so. Sorry. No, you're good. It's like. I was reading the 500 New York. And you yeah, I'll leave that. They're really good with process. Thank you.
Only thing I think the only thing I've left down is like,
I know my.
find where errors. Yeah.
Is that your seat?
Oh, it's me. Oh. Questions. Oh, all right.
Is there gonna be MBT or roles on the test?
Yeah, what we kind of did was mean value theorem. If you set average value equal to the instantaneous rate of change, that's mean value theorem.
Okay.
So number 2, part B is basically that.
Would you have solved that instead of just equaling?
If I were to give one to you where you have to solve, it'll be equal to 0, and then you can just go through inverse trig and solve. Yeah. Yeah, if you guys can put your name on your test review packets, stack them here. Just the test review packet, not the morning review. I was being through the test review. That's okay.
There's the packet?
Yeah, it's fine.
Okay.
No, don't worry about worksheet 4. Just, yeah, just the packet that has the problems that we have working.
Wait, is it still so you're right? Okay, sound good? Are you being helpful? Are you being generous? No.
This one or this one?
This one. That's what you. It's just the test review packet. If you guys can put your name on the first page, and then just turn in the test review packets next to the phones. And then eventually I need all your book bags under the phone as well.
No, my phone. I
You
can't.
can track with this.
Yes, I can calculate.
Did this also people? Oh, yeah, I didn't get the microphone, but everybody was like, already like almost done with it.
Everyone's supposed to say so good and it makes me kind of angry not why. Because there's
Yeah, make sure your names are on the test review packet, and then you can just turn that in. All right, all your book bags in the front. Page 11.